last time we talked about the history of the membrane developments, particularly focusing on the reverse osmosis membranes and the gas separation membranes. And today I think we will talk about the membrane preparation and characterizations. I think some of those materials may a little bit overlap with the previous ones, but I will go quickly through the concept of as an introduction. Okay? So the first slide might be what is the membrane? What is the membrane? What's the difference between the membrane and films? Membrane?
It's kind of selectivity.
Right. Membrane is different from film in terms of the transport property. Okay? If you have a transport of something, okay? Transport of ions, transport of mass, then I think we call that as a membrane. Whereas although you have the same polymer films or films, if you don't have any the transport property, we do not call that as a membrane. Okay? So membrane is different from film in terms of the structure, in terms of the functions, in terms of the transport property, mechanism, and the material construction. Okay? So membrane is different from film because we can separate some of the mixtures in the phase one, and you can selectively separate those mixtures, binary, ternary, quaternary mixtures through those some sort of films. Okay, but film is not the right term, as I mentioned. But in membrane-based processes, membrane itself is very important. Okay? Okay. Membrane material, membrane itself is the most important the material that we will need to talk about. Okay? So we have to, some Ju Sung told me about selectivity. Okay? Selectivity, permeability, or flux, or are very important transport properties of the membrane. Okay? If it doesn't select the mixtures, then there is no use of this membrane. Okay? It could be used to separate the material. You can use this membrane for energy production, and you can even produce the pure water and could be utilized for global warming and even for the seawater desalination, as we have just talked about last time. Well, this is the brief summary of structure of the polymer membranes. Okay? We have a symmetric membrane and asymmetric membrane. Okay? Symmetric membranes can be described as a dense membrane, as just we talked about the Wright and Breton's cellulose acetate thin film, which can separate the water from seawater. Okay, you can separate. You can go through the water can go through the cellulose acetate thin film. I mean dense film, but the flux is very low, but the rejection is pretty high, meaning that this film will reject the sodium chloride ion because of the little bit larger diameter of the ions. And I told you that ions are about 6 to 7 Armstrong, okay, in the case of sodium and chloride, if it's hydrated. But water molecules, if it's a single water molecule, the kinetic diameter is about only 2.8 Armstrong. Although it's clustered, it will be much different in terms of the size of those ions versus the water. So the dense membrane can separate the water and the ions, but flux is very low because this thickness is pretty thick at the time of Wright and Breton's invention. So Loeb and Surirajan tried to make a thin film, effectively a thin film on the surface, but support on the bottom made of the same material. Okay? And this is what they call the Loeb-Surirajan's asymmetric membrane formation. Right? Whereas you can make the porous membrane with a symmetrical geometry, and depending upon the pore sizes, you can make the you can use this porous membrane in microfiltration, ultrafiltration, and even the filtration purposes. Okay? You can make the ion exchange membrane or liquid membranes by filling or filling those pores with some of the liquids, which has some functions. And you can make the mimicking the anisotropic structure of this membrane with the same polymer, but you can have two different polymeric structure. The skin made of polymer 1, and the bottom, the support layer, made of polymer 2. Okay, you can have a polyamide layer on the top of polysulfone porous membrane. Okay? So various structures will function in different way. Geometry, depending upon the diameter of your hollows or capillary or tubular, depending upon the diameter of the materials. Yeah, thank you. So you can have a flash membrane or a hollow fiber membrane or capillary membranes, and depending upon the diameter of your outer dimension, we call this as a hollow fiber or capillary or tubular membranes. Okay? If you have a few millimeter or above, we call that as a tubular membranes. Okay? Flash membrane is one of the example. This is the membrane for a membrane bioreactor called MBL, and you have the flash membrane on both sides of the this module, and you pull the vacuum from the top, so that water will be passing through this flash membrane and come up to only the pure water will be passing through, whereas the larger biomolecules in the membrane bioreactor will be clogged, fouled on the surface of this the flash membrane. Okay, the driving force or flux are different, and depending upon the driving forces, you have different mechanisms or different mathematical formulations. But the mechanism or the equation is about the same. Where if you are dealing with the heat, then if you're a mechanical engineer, they are dealing with the Fourier equation or temperature gradient. Well, electrical engineers are using electrical flux, whereas chemical engineers are using the mass flux and the volume flux. Okay? So all the little different the molecules or molecular flux, but the equation is about the same. With the different applications. So we will talk about mainly the activity or the pressure. We'll use this pressure and activity and temperatures, and not much on the electrical potentials. Well, in terms of the membrane materials, I told you that in the membrane-based processes, membrane itself is very important. And you have to think about the membrane materials. The basic materials are polymers, metals, ceramics, liquids, and biological materials. And you have to think about the functional groups. And it does match, okay? It does match, but we can have ionic functional groups, or we can have geolites with very defined pores, or recently the MOF, metal organic frameworks, MOF, or COF, or PUF, you can name it with the different the crystal structures. We can put the chelating agents or selective ligands to ion exchange groups or polymers or whatever. But the polymers are different from metals and ceramics in terms of the composition of your organic atoms or metallic atoms or ceramic inorganic atoms, and also the crystallinity. Okay? The crystallinity is almost close to 100% for metals and ceramics, whereas the polymers are mainly semi-crystalline material. You have a crystalline portion and the amorphous portion in the polymers. Okay? And it's made of usually the organics, okay? The atoms. So the crystalline portions can be utilized for permeation, but remember that crystalline portion is not permeable, so that you have to think about the geometry, and so that finally the structural geometry is very important for metals and ceramics if you wanted to use these materials for the membranes. Okay? Biological materials can be utilized for membrane materials as well, such as chirosane or the liposomes, cell membranes can be utilized for membrane materials for separation and so on. So these are the basics of the membrane materials. If I will elaborate a little bit about the polymers, I put a few slides about the polymers. Okay? In polymer chemistry, we can see that you can have a homopolymer or copolymers, okay? And topolymers as well. Homopolymers are different from copolymers in terms of the number of monomeric units you have. Okay? If you have a polymer made of just one monomeric units, then it is called homopolymer. But if you have two monomers put together to become polymer, we call that as a copolymer. So copolymer means you have two monomers at least. Topolymer is the polymer made of three different monomeric, the composition. So in here we are talking about the copolymers because we have A monomers and B monomers. Now we have three different the copolymeric systems exhibited here as an example, and we have a block copolymer. Block copolymer is the one that which is different from homopolymer, where you have a A block and B block combined together to become a block copolymeric structure. The homopolymer, if you have a membrane with a homopolymer, and if you have a membrane from block copolymer, you can see the aggregation of those blocks are different from aggregation of the homopolymers. So recently, although it's difficult to make a block copolymers, you can make the self-assembly membrane and very unique layer by layer membranes out of these block copolymers, and it's a pretty hot topic from the scientists making the block copolymers. Okay, so it's not too bad if you have a block copolymeric systems, but be careful. Block copolymer is difficult to make, and membrane morphology will be changing as a function of time as well. So that's one of the good point and bad point about the block copolymer systems. And so far, although there is a lot of research papers published recently about the block copolymers, there is no real membrane out of this block copolymer in industrial applications. So, but anyway, in the future, I think if you solve some of the problems of the block copolymeric systems, you can deal with that. And I can show you later on, perhaps distribute those papers out of the block copolymer systems to you where I have the copies of review papers on this topic. Well, graft copolymers are the ones that you have A blocks or A homopolymer, whereas you have a branch made of the polymer called B. Okay, so you have a graft copolymer. Graft copolymer is called the branched polymer or branch structure, and this could be utilized as a brush, polymer brush, or comb type of polymers, so that you have a hair on top of the polymer backbone, and this might be a little different from just the homopolymeric structures, okay? Because if you have the material mixture, okay, in the aqueous phase will come through the surface of the membrane, and the membrane may have hair. Okay, so this hair will block the larger substances because of the increased entropy, of this hair, and so that you can reduce the fouling of the biological material on the surface of the membrane. Okay? Whereas the water can go through the basic polymeric structures. So the graft copolymer could be utilized for membrane materials as well. We can have a cross-linked structure. This cross-linked structure is different from the linear structure, as you can see here, because the linear structure will be combined together. So molecular weight will be principally infinite. Okay, so you have an infinite molecular weight polymer. Therefore, it will not be dissolved in any organic solvents in most of the cross-linked polymers. Cross-linked polymers are showing the resistance to chemicals, resistance to the heat, so that it will be utilized to have a much more high selectivity rather than permeability. Okay? So if you wanted to increase the selectivity, then you can think of cross-linked structure. Anyway, these are the basic information about the structure property relationships in polymers. We can talk about the free volumes, of course, in next slides, but this is the basic, knowledge that we have to deal with. In the case of polymers, we have to think about the stereospecificity or stereoisomerism, because if you're thinking about the vinylic monomer, we always have a substituent groups, such as a PVC or polypropylene. They all have a chlorine group as a substituents, or a methyl group as a substituent groups. If you think about the polyacrylonitrile, you have a CN group or nitrile group as a substituent groups. And these the geometry of the substituent group called AL, the position of this AL will determine your density. Okay, if you have an AL group in the same direction, toward the downward, or randomly distributed, or randomly distributed here in the case of atactic, or vice versa, or you have one on the bottom and the other one on the top, one bottom top, stuff like that. It's called the syntactic the geometry. Isotactic polymer is partially crystalline, whereas the syntactic and atactics are amorphous polymers. So crystalline and amorphous polymer may have a different density, so that your permeability will be quite different. You see, all the penetrants, penetrants can only pass through amorphous region. Therefore, atactic polypropylene, for example, has a much higher permeability than isotactic polypropylene, for example. And this is one of the example of the things that you have to think about it in the structure property relationships of the polymers. We have to think about the glass transition temperature. Glass transition temperature. And the next slide, I will tell you what's the definition of TG and TM. But you see, depending upon the substituent groups you have in the vinyl group, okay, if you have a hydrogen only, we call it as ethylene. If you have the methyl group as a substituent, then we call it as a polypropylene. If you have the benzene, there is polystyrene, vinyl chloride, the acrylonitrile. And if you have four the F groups or fluorine groups, we call it as a PTFE, polytetrafluoroethylene. Polyethylene has minus 120 degrees C as a glass transition temperature, whereas if you have substituents, which has a little larger, meaning that if you have increased in the size of your substituent groups, or the with the charges or dipoles, you can increase your glass transition temperatures. Okay? Of course, it doesn't tell us about the melting. It doesn't tell us about the crystallinity, but it tells us the glass transition temperature is quite different. Now, TG is defined as the temperature where your amorphous portion will be melt. Okay? Actually, that's not exact definition, but the melting temperature is defined as the temperature where your crystalline portion will be melt. Okay? Whereas amorphous portion will be moving, okay, so that you have a long interchain distance will be moving anyway before the melting is defined as a glass transition temperature. So TG is very important in membranes for particularly for gas separation, okay? And it affects the permeability and the selectivity as well. So if you have a high TG material, then you decrease the permeability, whereas you increase the selectivity. And this is one of the example of the importance of the TG. Now, TG can be measured by the dynamic mechanical analysis, or you can measure TG by the DSC, differential scanning calorimetry. But in terms of the modulus in y-axis, you can see this is the storage modulus, and x-axis will be the temperature. Okay? So if you increase the temperature, your modulus will decrease in some different fashion. Okay? Now, in the case of crystalline polymer, the glassy material before the TG, okay, you have a pretty high the modulus, whereas if you pass the TG, you still have the solid state, but the modulus may decrease depending upon your material stages. Okay? If it's a crystalline polymer, the modulus will not change, because in the case of crystalline polymer, you only have crystalline portion. You do not have amorphous portion. Okay? So the below TG, you have a glass state, and above TG and below TM, and so in between TG and TM, it is called the rubbery state. Rubbery state is governed by the portion of amorphous materials. So if you have an amorphous region, then your amorphous portion will be moving, so that thermal motion will decrease the modulus of the polymer, and so that modulus will decrease largely for amorphous polymer, whereas you maintain some crystallinity Therefore, the semi-crystalline polymer will follow this line, whereas crystalline polymer will not change its modulus, but will decrease its the modulus above the melting temperature, because melting temperature, again, is defined as the temperature where your crystalline portion will be enormously moving. Okay? So that it will change it from solid state below Tm up to the liquid state above the melting temperature. The modulus can be detected by the dynamic mechanical analyzer, so that you put the film or sheet over the films and apply the dynamic the waves, okay, as a function of temperature. So along the inside of the heat chamber, you increase the heat frequency or change your wave number, so that vibration will detect the modulus changes of your material as a function of temperature. You can, this is the basic knowledge about the polymer, just in case. You have to think about the molecular weight. Okay? Molecular weight is important because if you make the membrane, polymer membrane, out of low molecular weight components, you will not be able to make the films. You will not be able to make the membrane, okay, for right geometry. In other words, you cannot spin the hollow fiber with the polymer, from the polymer with the low molecular weight components. You cannot make the flash film, okay, with the polymer, from the polymer with the low molecular components. So there should have been a certain molecular weight the criteria. That's why we have to think about the molecular weight. Well, molecular weight is defined as average molecular weight in polymers, because as you have seen, the A and B type of polymer, AAA or BBB or whatever, you have to have a certain the chain length, okay? Whether it's made of polycondensation or whether it's made of addition or radical polymerization reactions. So you have to have a certain number of repeating units. Now, during the polymerization reactions, the unit that is attached to each other will be different in number. That's why we statistically define the average molecular weight. Now we can have 4 different ways of averaging this molecular weight, and we can introduce the 2 of them. Okay? We have first of all the number average molecular weight and the weight average molecular weight. You have a subscript n representing number average, whereas weight average is defined as MW, and you put bar on top of M as an average. Okay? So M and bar is called the number average molecular weight of a polymer, whereas MW bar is called the weight average molecular weight. And this is the definition. Okay? By definition, always MW bar is larger than Mn bar. Okay? So the distribution of a polymer from your batch is described here in this case, okay? And always MW bar, weight average molecular weight, is larger than Mn bar, whereas the number maximum of this distribution is always defined as the number average molecular weight. If you have a very narrow distance between the Mn bar and Mw bar, we call that as a narrow molecular weight distribution of the polymer. So the distribution will be pretty close, because this is Mn bar, whereas Mw bar might be somewhere here. Okay, if you define mw bar divided by mn bar is very close to 1, we have a monodisperse polymer. If it's greater than 1, we call this as a polydisperse polymer. In this case, mw divided by mn bar is greater than 1 because mw bar is much larger than mn bar. Now, there has been experiments in making polymers in the space and in the earth. Okay? Now, if you polymerize your polystyrene from radical polymerization in the earth and in the space, okay, you can have a different dispersity. Okay, in other words, in the space you do not have the gravity effect, and if your environment is not affected by the gravity, then you can make the monodisperse polymer, whereas because of the gravity effect, we always have the polydisperse polymers in this case. Anyway, we can think of mw bar, and usually mw bar should be greater than 100,000 in order to make the successful membrane fabrications, okay, as one of the rule of thumb. So mw bar should be greater than 100,000 is one of the criteria. Now we have to think about the free volume. Free volume is the one that if you increase the temperature, your specific volume is plotted here. And if temperature is going back to the Kelvin temperature, if you have a Kelvin temperature is equal to 0, then there is no specific volume. And the volume will increase as a function of temperature, perhaps linearly, okay, up to the gas transition temperature. Above the gas transition temperature, your polymer will move and follow this line. And the point where you have a change in the slope is called gas transition temperature. The reason why we have TG is that if you have a side chain and if you have a long polymer, you have an amorphous portion. This amorphous portion may have some length of the segments, and these segments will be moving, okay, in the amorphous portion. So those amorphous portion will be moving so that you have an increase in the free volumes. And this is the point that I have defined as a point where amorphous portion will be melting, but not melting, but moving. Okay? So that's why you have the increase in free volumes above the gas transition temperatures. Now, we may have a melting temperature somewhere above the gas transition temperature, and the phase will be changing from solid state below Tm to the liquid phase above Tm, so that there is an abrupt change in the slope. So it will be discontinuity from the point here to somewhere. Anyway, free volume is always present in the polymer below the melting temperature and the solid state. Okay? We can describe this free volume in some way, which is called the Ferris equation, so that you can measure the free volume. Okay? Anyway, if you have those gas molecules passing through the polymeric films with a dense structure, okay, you do not have any pores or cavities. That's what the conventional definition. but you may have free volumes. Okay? Those free volume elements were not regarded as pores, but recently, for the last 10, 15 years, there are some methods or characterization methods developed so that we can detect the free volume contents. We can detect the size of the free volumes. Therefore, we can define these free volume elements as cavities, or in some cases, pores. Okay? Traditionally, the pores were not. Traditionally, the pores were not present in the dense films, but we knew that how many free volumes present in the dense films, and what are the distribution, and so on, by using the positron analysis. So I can introduce you what is the positron. But anyway, we can detect the free volumes, and this is the traditional definition of the free volume concept. But if you have a high free volume polymer, your permeability is pretty high, whereas if you have a smaller free volumes, then there is not much volume or path for the penetrance to go through. Therefore, the permeability is quite low. Okay? So the free volume size, and the distribution will be very important for gas separation membranes and so on. Now, there are some methods developed recently at Hanyang University at the Industrial Engineering Department. He is a mathematician, and he developed some method of what's called the Voronoi diagram. And Voronoi diagram can detect the logical way of detecting the free volumes in mathematical way. And he showed us, and he can, if we provide the structure of the polymer, then he can provide us what is the free volumes, okay, without measuring the density and so on. And we would like to correlate our method, our detecting method, with his Voronoi diagram, and perhaps there will be a new way of detecting the free volumes. Okay, so those are the brief introduction of the polymers. And again, the membrane processes. In membrane processes, most important part is the membrane itself. Okay? Membrane have a different structure, different function, and so on, and so that these all membrane itself will determine the property, transfer properties, of course. Okay. Now, from now on, I think we can talk about how we can make the membrane. Okay, not the polymer. Okay? We can make a membrane from polymers, metals, ceramics, and so on. And we have to think about how we can make the membranes. We can make a membrane by, coating, deep coating, just like the ones that I have introduced to you about the Loeb reagent membrane. We can make a composite membrane by interfacial polymerization, or we can make a deep coating. We can make a plasma polymerization on the top of the support layer. We can make a hollow fiber by a phase inversion called the NIPS, okay, NIPS process, non-solvent induced phase separation, or TIPS process, temperature induced phase separation, or vapor induced phase separation, and so on. So you can make a membrane out of this phase separation. We can make a sintering process to make the membrane. Sintering means heat treatment. Okay? Heat treatment above the melting temperature. So if you have metals or ceramics where they are crystalline materials above the melting temperature or close to the melting temperature, if you apply the pressure, then those particles will gather together to become agglomerates and can make the membrane. So powders will become membrane by using the sintering technique. And the next slide will be showing the sintering technique as well. We can have an irradiation and track etching process. We have a slide, so I will introduce to you. Okay? I will introduce to you all from the sintering to the rest of these techniques. We have, we can make membranes by characterizing the membranes, and the transport property will be determined by morphology. So the morphology is very important, okay, for the transfer properties. Mechanical property and chemical property and electrical properties are very important for the membrane formation as well. Okay? Although you make a film, you make a hollow fiber, if it's not, strong enough, then you cannot make a membrane modules. So mechanical properties are very important. Chemical resistancy, electrical property will be important for some applications where the resistance is required. So membrane material, membrane itself is important, I said, and the membrane materials, whether you have a polymer, whether you have a choice of metals, whatever, the membrane materials are very important. And this membrane material may have a different membrane structure with a different porosity, pore size distribution, okay? A symmetric structure will determine your membrane applications. Okay? So these are the three very important parameters. For example, gas separation and evaporation membrane requires a very thin layer or a very dense layer on the top, at least, of your membranes. And in that case, membrane materials will determine the separation performance of this gas separation and evaporations. Whereas if you are using the membranes for microfiltration and ultrafiltrations, of course, your charge or surface layer is important, but membrane structures such as porosity, okay, pore structure will be much more important than membrane material itself for microfiltration and ultrafiltration purposes. So we have to think about the materials, structure, and applications. Now we need to think about the selectivity and permeability. Okay? Selectivity. I told it in the first slide that membrane will and should separate something. Okay? Should separate something. From the binary mixture, only one of the components will pass through, so that we can determine what is the selectivity of this membrane. Okay? If the selectivity is 0, then you do not have any selectivity, so that it will not be passing. If the selectivity is 1, if the selectivity is 1, that means that you have a pretty larger pores, so that both of these two components will be passing through. The rate of passing the one molecule or one component versus the rate of passing the second component is about the same, where we have selectivity is equal to 1. So if the selectivity is about 10, then means that the rate of permeation of first component is about 10 times larger than the rate of permeation of the second component. So the selectivity is very important. The selectivity is determined by the physical properties and chemical properties of the materials. For example, if you have a flexible material with a low Tg, then usually the selectivity is quite low. Okay? Because you have a free volumes, okay? Free volumes, amorphous polymers or free volumes. You have larger pores, large cavities, so that there is no separation property. There is no selective properties of the materials. But if you have a rigid material, and if you have aromatic backbone materials, your selectivity will increase. So the selectivity is very important and could be determined by the structure of the polymers. Permeability is very important as well. The permeability it could be determined by the cross transition temperature and the flexibility, of course. If you have a highly flexible material, permeability increase will selectivity decrease. And of course, the porosity is influencing this, the permeability. If you have a dense membrane, permeability is quite low, whereas if you have a porous membrane, then permeability is quite high. Now, other than the flexibility, we can think of crystallinity as well. Okay? If you have a crystalline polymer, then the selectivity is high, but permeability is quite low. Okay? Because the penetrants can only go through the amorphous portion rather than crystalline portion. So permeability is determined by the amount of amorphous portion, or the amount of crystal portion. Okay. Now, when we have a rigid chain and aromatic chain, we increase the selectivity, but decrease the permeability, of course. Okay. But, and also these polymers with the rigid chain and aromatic chain will increase the thermal stability and the chemical stability. For example, we have a polyether imide called ULTEM, and it has a very high strength and rigidity at elevated temperatures. But you lose, if you increase the stability, then you lose the processability. Okay? So it's not that simple. So you have to think about various factors. Okay? Various factors, other than just the free volume, just the aromatic structure, but you have to think about the processability. Okay? So you need much more experience than just the knowledge in the class. Okay? If you wanted to make a porous membrane, we can have a symmetric structure and asymmetric structures. Okay? Usually, the asymmetric structures are required in the case of little smaller pore size on the top. Okay? If you have a smaller pore size made of polymer or ceramics, we can have ultrafiltration proposed. If I have larger pore sizes ranging from a few hundred nanometer to tens of microns, then we have microfiltrations. Ultrafiltration requires only about a little bit of around 10 to 20 nanometer in pore sizes. You can make films. You can make several preparation processes where sintering, extruding, irradiation, temperature plating, phase inversion, and so on. So we'll talk about these membrane preparation processes. First of all, sintering. Okay? Sintering method can be applied for crystalline material. Okay? So that if you have a powder with the crystalline formation crystals, those crystal powder will be heated to become agglomerated, to become a little larger in size, so that they can form the membranes. But between these agglomerates, you may have a little bit of pores, so that through those pores, you can make the membranes with the pores. For example, if you have a metal powder, then you can make the stainless steel, porous stainless steel membrane or whatever, okay, or support. Or if you can have aluminum oxide, then you can have aluminum oxide nanotubes or tubes. If you have graphites, usually the carbons are amorphous or crystalline depending upon your preparations. And if you treat them at high temperature along with the glass, then you can have some sort of a crystalline portion. But between those holes, you can use these holes for separations. Okay? For polymers, such as a crystalline polymer, PTFE, polyethylene, polypropylene, they all have crystalline portions, although TG is low in the PE and PP. But PTFE has a melting temperature around 330. PE and PP has a melting temperature around 150. So above this melting temperature, or around this melting temperature, you can sinter them, okay, and combine them together and stretch. If you stretch them, you can make some macropores with a few microns to a few millimeters, so that you can use those holes for separation purposes. For example, you can have some holes here, okay? You can have some holes after sintering, and these will be used for filtration of colloidal solution, gases, or isotopes. Okay? And these are the examples of the sintered membranes. Another example is the PTFE, polytetrafluoroethylene. And PTFE has a melting temperature around 330 degrees C. So when you increase the temperature of this PTFE powder and pressurize them and stretch them, okay, then this fibrilla structure, fibrils will be stretched, so you can make a dark region, which is pores or macropores, okay, in between these the stretched lines. And this PTFE is white in color and could be used as tapes, right? Wrapping up your pipe, metal pipes in your water line, or could be used in many applications. So because this is very hydrophobic, you can use this PTFE membrane for membrane contactors, as Professor Drioli have mentioned already, I guess, and could be utilized for membrane distillation, could be utilized to separate something, okay, and so on. In some cases, in some separation purpose, they do not want hydrophobic surface, so they sometimes make the hydrophilic surface out of this PTFE membrane by plasma polymerizing or surface treating and so on for some purpose. I think you can take a look at some of the other applications. Track etching method is the one that you have two processes. First of all, you have a roll of films, and it's passing through this beam line, and there is a high energy ion beam is bombarding through the films, such as polycarbonate, amorphous polymer. And if you put the beams, then beam will penetrate through. Beam is like an X-ray. Okay, depending upon your energy intensity of your beam source, you can penetrate through. So, so after bombarding these ion beams, then in the second phase, it will be put into some solution, okay, liquid solution such as sulfuric acid. Then past the line, beam past the line, beam past the region will be etched so that you can make a hole out of this. And these are the regions where your beam will be passing through. So the ion beam intensity will determine how many holes that you have, and the etching time will determine the length of your holes as well. So the pore density, your pore density, in other words, how many pores you have on the surface, is determined by the residence time of the irradiator, and the pore diameter is controlled by the residence time in the etching bath. So by controlling those intensity and the time in your etchings, you can make the porous membrane or the less porous membrane. It's like a drilling, drilling your films. And track etching method does not produce the homogeneous membrane, homogeneously distributed pores on the surface, as you can see here. But the advantage of this track etching method is that you have a very fine pore with the same size. With the same size. You see, the size of this is about the same. So that it's very important because you have a very narrow pore size distribution. Not the molecular weight distribution, but pore size distribution is quite narrow. And it's very important because if you have some sort of mixture in the aqueous solution, for example, then only the penetrance with a less in diameter than this pore will go through, whereas the larger molecule than this pore will not go through. So you can have a very definite the molecular separation using this track etch membrane. So this is widely used in biomedical applications. There are only few countries making this track etch method membranes, but polycarbonate is one of the very important example. And PET, polyethylene terephthlates, and polycarbonate are the, I guess, two examples that you can use. We can make the dynamic membranes. We can make a dynamic membranes. Dynamic membrane can be made by hydrolysis by many methods, of course, but can make the in this way. If you have some acrylonitrile, polyacrylonitrile membrane, for example, and if you put this polyacrylonitrile membrane in sodium chloride, sodium hydroxide solution, then it will hydrolyze to become polyacrylamide. Through hydroxin formation. Okay, you have an intermediate formation, which I did not, write in the structure. The color changes from the white to yellow, so that by looking at the color changes, you know what is the depth of the hydrolysis of polyacrylonitrile to polyacrylamide layers. In other words, if you have a polyacrylonitrile membrane, okay, you first make a polyacrylonitrile membrane, and your surface might be put into the sodium, exposed to a sodium hydroxide solution, okay, and later on you will remove those sodium hydroxide, then only the surface of those polyacrylonitrile will change into polyhydroxylamide, acrylamide. Or if you have a roller of polyacrylonitriles and put it into the aqueous solution and dry them, then you only treat the surface of this membrane, or you can totally change the structure from acrylonitrile to polyacrylamide, depending upon the soaking time or immersion time. So this way you can make a different membranes, okay, with different structure, different functions. Because polyacrylonitrile is relatively hydrophobic than polyacrylamide, because you have a carbonyl and amine group, so that this has much more capability to have a hydrogen bonding with water, so it becomes more hydrophilic than this polyacrylonitrile. Of course, the crystallinity is different, but you change your the chemistry as well as the morphologies. So this is one of the examples, and you can make a dynamic membranes in this way. Second way of making your membrane is a phase inversion. Okay? Phase changes. Phase changes from one stage to the other stages. And we will extensively talk about and discuss about this phase inversion, of course, because this is much more versatile than the rest of the membrane preparation methods. Using this phase inversion method, we can make the membrane with different morphology. You can make a porous membrane or less porous membrane, or you can make a symmetric membrane or a symmetric membrane, depending upon how we can manipulate this phase inversion. Usually, when we use this phase inversion, polymer is used mostly. And we have a polymer-rich phase and polymer-lean phase. Okay, less polymer phase, in other words. Polymer-rich phase will make the membrane. Polymer-lean phase will make a pore. Okay? Because polymer usually is dissolved in solvents. Okay? You have solvents. And for example, if you have a 30% polymer in NMP as a solvent, then 70%, for example, weight, of course it's a weight percent basis, but 70% is polymer-lean phase, and 30% is a polymer. Okay? So when you cast a membrane on top of the glass plate, and if you evaporate those solvents, NMP, 70%, your thickness will become 30% of your first initial thickness of a solution, okay? Because 70% of your whole thickness of your casting solution will be removed by evaporation. So basically, you have a reduction of the thickness of a casting, so the thickness to basically the weight percent of your polymer. So you can make a membrane out of this polymer-rich phase. But if you add the non-solvent, okay, so when you remove those solvents or polymer-lean phase, then you can make the dense films, okay, just like Wright and Breton's cellulose acetate dense films, which can separate the sodium chloride and water, but the flux is quite low because your thickness is quite thicker than what you can expect. Okay? The Loeb and Sory-Rajan devised a way of making a thin symmetric membrane by evaporating a very short period of time, okay, like 10 seconds, and then put it into water, which is non-solvent, and can make the phase inversion from the liquid phase to the solid phase by coagulating or precipitating these polymers. And in this phase inversion, we have NIPS, non-solvent induced the phase inversion, phase separation, called NIPS. We can use the temperature as one of the driving force for phase inversion. You know, if you put the solvent in the polymer, we do not call that as a solvent, but we call that as a diluent. Okay, so that polymer will be becoming, above the critical temperature, so it becomes the liquid phase. If you decrease the temperature, it will solidify. It will be solidified, so you have a liquid and solid, critical region passing, or called the binodal region, so that you have a phase separation between the liquid phase to the solid phase due to the temperature difference. Okay? So that's what we call temperature-induced phase inversion or phase separation. Or you can induce this phase inversion by vapors of water. So water vapor will be spreading on top of the polymer solution, so that the vapor will induce the phase separation. It's called the VIPS. Or evaporation-induced phase separation is just evaporation. You can just evaporate these solvents so that you can make the dense films out of this. Rest of them are the ones that you can make the porous membrane or symmetric membranes. Okay. Okay, so let's talk about the evaporation. Well, evaporation is the one that you have a polymer solution. For example, if you have a 38% polymer and 70% solvents, 70% of solvent will be evaporating, so that your final thickness of a membrane after complete evaporation of solvent will, of course, determined by the weight percent of your polymer, so that you have dense films. Vapor-induced phase inversion is the one that first you cast the films, you cast the solution, and this was exposed to the water vapor, so the water vapor will induce the precipitation of your polymer, because water will be usually non-solvent to the polymer. Okay? So they can make the porous membrane out of these VIPs. Now this VIPs has not been commercialized yet, okay? Although VIPs is quite sometimes used in the literature, but the VIPs has not been utilized in the commercial scale, because it's not easy to control the vapors in a reproducible way in the larger scale. Small scale, it's okay. So we have a VIPs machine in upstairs in 10th floor, but it's only about this size, about table size. Okay? We knew that this is not really important, but I think it could be utilized in the literature anyway. Temperature-induced phase separation is the one that you first make a polymer solution at high temperature, and if you decrease the temperature, then you can induce the crystallization of polymer, so that you can make a films out of that. In some cases, usually the dip tips is quite typical, but in our case, in our case, the research at the 10th floor with the Solvay, we have both tips and nips process by using the novel solvent called the polacrene where this polychlorine is water soluble. In other words, this process has been known for PVDF membrane fabrication with the non-water soluble diluents such as DOP or DBP, so that when you decrease the temperature, you can just induce the crystallization. Okay? And then later on, after membrane formation, you can dilute them. You can remove those diluents in some way. But in our case, because we are using water-soluble diluents, we have both nips and tips all at the time you decrease the temperature. So it's a little different from what the others have done so far. Anyway, I think we can talk about in more detail about these tips later. NIPS is the one that you have, you first make the EIPS, okay, for a polymer solution, and after some time, you can put those, the liquid phase into the non-solvent, so that solvent will be exchanged with non-solvent to make a films. Now, film thickness might be about the same as the polymer solution thickness, depending upon how long you evaporate your solvents. And this is the symmetric membrane. And you can detect the pore structure with the SEM. Surface is usually does not show any distinct surface structure with the pores. If you have a pore, then you have some holes, but it doesn't have any distinct structure. Cross section is the one very typical, and this was made from PEEK, polyethyl ketone, with some novel crystalline material, and use the chloroform as a solvent. They can just evaporate the chloroform and make the films, surface and the cross section. It do not have any pores. This is the example of dense films. And you can make the porous films, and this is the surface, and perhaps the cross section might be the same geometry. You can make a symmetric membrane out of polyethyl sulfone or PVDF. Or you can make the cellulose acetate or cellulose nitrate, and so on. And this was induced by water vapor in this case, by VIPS process. So these are the examples of symmetric membrane or asymmetric membrane. In this case, symmetric as well, particularly from the VIPS. So depending upon what is the density of your water vapor exposure, you can make the less porous or more porous membrane in this way. So this is the example of the membrane preparation, and we will continue our discussion next week about this membrane preparations. It's about over 200 slides, so please read. You can just look through what I will talk about. Any questions, comments? Okay, if you don't have any question, then have a nice weekend, and I will see you on Wednesday.